Bismillahirrahmanirrahim. I welcome all the engineering students, especially the students of Khwaja Farid University of Engineering and Information Technology in this course of Engineering Dynamics. Dear students, we have discussed the linear momentum and the change in linear momentum, that is called the impulse or linear impulse, and the rate of change of momentum is called force. So in the previous lectures we have discussed the linear momentum and the change in linear momentum, that is the linear impulse, and we have solved the problems regarding the linear momentum or the conservation of momentum, and we have also discussed the change in momentum is called the impulse, that is initial momentum plus the impulse is equal to the final momentum. So today we will discuss the angular momentum. So we talk of, inshallah, the angular momentum and angular impulse and some of the problems to be solved today. So dear students, so let's talk of the angular momentum. Basically the moment of the linear momentum is called the angular momentum. So for example, if you see, this is the origin, this is x-axis, this is y-axis, this is z-axis, and this is the distance r, and the body is moving in this direction. This is the direction of the linear momentum. Now the moment means torque of this linear momentum about this point is basically the angular momentum. So it is just like we have already discussed what is moment is r cross f. So here it is r cross the mv, the linear momentum, and this is the direction of the linear momentum. So that's angular momentum, and angular momentum is a vector quantity as it is a cross product. So angular momentum is basically a vector perpendicular to the plane on which the moment is being applied. Hence very clearly you can see that the moment of a linear momentum is called angular momentum, and angular momentum is perpendicular to the plane. So angular momentum is basically r cross mv. So therefore we have to take the cross product of these two, and that is the r, and this is basically my this is the components of just the m, I, j, k. You know that the cross product x, y, z are the components of the r, and vx, vy, vz are the basically the vector component in the linear momentum, and mass is constant. When you open up, of course, this determinant, you get this. You know the determinant, how to open up. Let's take I, that is y into vz minus z into vy, right, and so on. So if you see here, if go to if I went to the scalar method to find the angular momentum, let's see, this is the body here. It's moving in this direction. Of course, the linear momentum is this direction, and in making an angle theta with the r. Now if I need to find the angular momentum, means the moment of this momentum about point O, I extend it, and this becomes the perpendicular distance r sine theta. You know that by from the previous knowledge of the moment basically is the r times f, and in the case of, if I take the scalar method, then it is a perpendicular distance between the line of action of force and the point of rotation is called arm of force r. So this is, if this is r, this is a sine component. So it becomes mvr sine theta. Okay, if the moment, of course, in this I show you in a plane, but if it is a three-dimensional, of course, so this is my x component of the angular momentum, this is the y component of the angular momentum, and this is a z component of the angular momentum, that hx, hy, and sz. Okay, angular momentum of a particle in a uniform circular motion. For example, if a body m is moving with a constant velocity and having a radius constant, right? So the angular momentum vector point out of the diagram is moving outward from the diagram, coming out of this plane, coming out of the computer screen. So this L is equal to Rp sine theta. P is the linear momentum. So of course this is R. We take that component of R which is perpendicular to this. So it is Rp sine theta, the MVR sine of 90. In this case the angle between R and V is 90. So therefore it is simple MVR. So when a particle is moving in a uniform circular motion, of course the angle between the R, the arm of force, and the velocity is 90 degree. So therefore it is simple MVR. Similarly, angular momentum of a system of particles, if there are more than one particles, we just take the angular momentum of every particle and then sum it together, you get the total angular momentum. But angular momentum should be added as a vector. It is not like a simple simple addition. So we take the by head to tail rule and we just add just like we added the linear momentum. Linear momentum and a force, you know that the rate of change, the time rate of change of linear momentum is called force, where P is mv, and the impulse is the product of force and the time, or is equal to the change in momentum. This same analogy is being used in the case of angular momentum. So the time rate of change of momentum is called force and the change in momentum is called impulse. Similarly here, the time rate of change of angular momentum, dl by dt, is called torque. So torque and length both are being calculated in the same units. So it's very simple. The rate of change of linear momentum is called force and the rate of change of angular momentum is called torque. And the unit of torque is Newton meter and the unit of angular momentum is also Newton meter. In this case, remember that the origin is not accelerating. Origin is constant and we are taking the angular momentum with reference to the fixed origin. Now, rate of change of angular momentum, you say change in momentum is R into R cross F or R into mv, right? Mv dot. Mv dot is a change in velocity. Rate of change of angular momentum, right? Rate of change of angular momentum. So if I say h naught dot is equal to R dot plus mv, if I take the derivative, so it is R cross mv. So first we use, if R is also changing, it is not moving with uniform radius, then of course the two terms are there. One is the radius and one is the velocity. So I take the product formula R dot into mv plus R into mv dot. This R dot is v plus mv and this is R cross mv dot. So the term R cross mv is 0 since the cross product of parallel vectors is identically 0 because the angle between them is 0 degree and sine of 0 is equal to 0. So summation of m means summation of moments is equal to the rate of change of angular momentum. So momentum about the fixed point O of all the forces acting on m equal the time rate of change of angular momentum of m about O. So again I say the rate of change of the angular momentum is basically the moment. And let's talk of what is the change in angular momentum. Dear students, the story is here the same thing. T1 to T2 is summation of m naught dt, where moment applied for a small period of time. If we integrate, that is equal to the change in angular momentum. Just like in the case of linear momentum, the change in linear momentum is called linear impulse. Similarly here, this angular impulse is the change in angular momentum. Let's move to the units of angular impulse, right? So if I go to the units of angular impulse, this is Newton meter, that is my torque or moment, into second. Or I can multiply with meter and meter, I can kilogram meter square per second. If I put kilogram is meter per second square, and this second cancel out, we can also find. So in SI units, of course, the unit of moment is Newton meter and into second. If I put the value of Newton into basic units, so of course the kilogram meter per second square, so it becomes kilogram meter square per second. These are the SI units. As far as I talk of the FPS or US units, it's a pound fit. A fit pound is a unit of moment, and that second is a unit of time. These are the units of the angular impulses. Again, the change in angular momentum is called angular impulse. So the same angular impulse moment principle, the change in angular momentum is called impulse. So the initial momentum about a fixed point plus this is the impulse t1 to t2 summation of mo into dt is equal to the final momentum. Or if I say in the two plane, so mvzy minus yz vyz at 1 plus the impulse is equal to the angular momentum at the other position. Conservation of angular momentum, if I say the angular momentum is of course conserved for a isolated system, so the change in momentum is 0 or the initial momentum is equal to the final momentum. Let's move to the simple problem 3-24. A small sphere has a position and velocity indicated in the figure and is acted upon the force F. Determine the angular moment h naught about point O and the time derivative h naught dot. So this is the body and applying the force F in this direction, and of course R we take, this is the position. If I say the xy coordinate of this object, I can show it very simply, that is this is 3, 6 and 4. So this is my R. So I will take R cross mv and we can find out the angular momentum. Whenever you are talking of in 3D, it is easiest to use the vector method is R cross mv or R cross whatever in 3D, it becomes easy. So h naught is equal to R cross mv. So I get the R, of course 3i plus 6j plus 4k. Right? Similarly, this is next the of course mv. The mass here is given to you 2 kilogram, right? And the velocity is only in y direction. So it is 5j. So dear students, now it just becomes 10j. Now I cross j, use this circle, it becomes k. If the next vector is third one is along the motion is positive, or it is up in the opposite direction of the motion, it is negative. We mostly take clockwise. Right, j cross j is 0 because angle becomes 0. Then k cross j, this becomes minus I. It becomes minus 40i plus 15k Newton meter per second. This is the vector method. This is the moment, angular momentum in x direction. This is the angular momentum in y direction. Now we can also find out the rate of change of momentum. The rate of change of angular momentum is the moment or torque is equal to moment or torque. So h naught dot is equal to m naught, which is equal to r cross f. This is r and f, this is the force 10 Newton in z direction. So if I cross k, you see I cross k is minus j in opposite direction. Then j cross k is positive direction I and k cross 0. So finally the 60i minus 30j Newton meter. So this is the rate of change of angular momentum will give you the moment. Simple problem 3-25. A comet is a highly eccentric orbit shown in the figure. Its speed at the most distance point, at this point A, which is at the outer edge of the solar system, is 740 meter per second. Determine its speed at point B of the closest point to the sun. This is an elliptical path, and the distance at point A, the distance from the sun is 6,000 exponent 6 kilometer, and of course from the B point at very close is 75 exponent 6 kilometer. We need to find the speed of this object, comet, at point B, which is near to the sun. So VA is 740, what is VB? So law of conservation of angular momentum, momentum at A is equal to momentum at B in reference to O, because the sun is constant at the stationary position. So MRAVA is equal to MRB The question is, why you are not taking the R? Of course, R is changing, but the angle is 90 degree, therefore it is the same. So MM cancel out, so VB is equal to RA, VB, RB. So 6,000 exponent 6, 740 divided 750 exponent 6, I get it 59,200 meters per second, or 59.2 kilometers per second. Simple problem 3-26. The assembly of the light rod and two end masses is at rest. When it is struck by the falling wad of putty traveling with the speed of V1, this one is moving, and they strike on this mass, determine the angular velocity theta 2 dash of the assembly just after the impact. The pivot at O is frictionless, and all three masses may be assumed to be particleless. Particles, they are particles. They can be considered as all the masses are concentrated masses, rigid bodies. So let's see, we are ignoring here the impulses associated with the weight during the collision process. We ignore. So we say the angular momentum remains same. h01 is equal to h02, are taking the moment in the rightward direction. So that's the first moment. Of course, mvr. So this one is mv1l. This one, small mass mv1 into l. This is the first angular momentum, is equal to the momentum of this one, this body after this, m plus 2m, right? M plus 2m, and then it has a m plus 2m, and arm of force is l. Then there is a velocity v is equal to r theta l theta 2 dash. The angular movement, the angular velocity, because this body will rotate like this and then come back with this swing. So this is the moment on before the collision is simple. The moment, angular momentum is only of the small mass, then it is a larger mass, and then we move to the other side. It is 4m, right? This is m, r, v, r is 2l, and then there is a velocity which is r theta dot. R is 2l theta 2 dot. So here we just of course ml is common, cancel out. V1 is equal to 3l theta 2 dot plus 16l theta 2 dot. Simple L theta 2 dot is V1 over 19l, and that is in the clockwise direction because I'm taking the clockwise positive. If I know the initial the velocity of the putty and the length, we can find out the angular velocity, that is in radians per second. Let's move to the sample problem 3-27. A small mass particle is given an initial velocity v0 tangent to the horizontal. It is giving the velocity v0 tangent to the circle, right? It's just slightly below this hemisphere, tangent to the horizontal rim of the smooth semi-spherical bowl at a radius r0 from the vertical center as shown in the point A. As a particle slides past point B, a distance h below A and a distance r from the vertical center, this point B is slightly lower on the periphery of this hemisphere. So this height is h, right, from the vertical central line. Its velocity v makes an angle theta, angle theta with the horizontal tangent to the bowl through B. Determine the angle theta. Dear students, of course, again, law of conservation of angular momentum. Initial momentum is equal to final momentum. So mv naught r naught is equal to mv cos of theta, because here we are talking of this component, because moving because of this tangential velocity component. So also the energy is also conserved. E1 is equal to E2. T1 plus V1 is equal to T2 plus V2, half mv naught square plus mgh initially, and T2 is half mv square plus 0, right? Because final potential energy is 0. We are taking this one as the reference, so therefore this we are taking the potential energy. Initially it is there, and finally it is 0. If I take the reference from the above, then of course reverse process will take place. So here mass is cancelled out, and we just simplify here V naught square mgh V square, V is equal to V naught under root gh. This is the V initial velocity, and g is known, h is known. Now eliminating V and substituting this. Here students, you see this diagram, this is h, this distance from here to here is r, so this, r naught, this is r. By using this triangle I can say r naught square h. So r naught square, Pythagoras theorem, hypotenuse square is equal to base square plus perpendicular square, or r square is equal to r naught square minus h square. So keeping these things in view, so what we have, V naught r naught V cos of theta r. Put these values in equation number 1. So V naught r naught, then it becomes V is equal to, we have find out, V naught square plus 2gh. I'm sorry here I missed the 2 here, please put the 2 because this 2 is multiplied with this. Then we have we have r is equal to r naught square minus h square cos of theta. So from here you find the value of cos of theta. Theta is equal to cos plus r naught V naught under root V naught square plus 2gh under root r naught square minus h square. So very simply I can take V naught divide with V naught square, and then it becomes 1 plus 2gh by V naught square, and V naught cancel out. Then I divide with r naught square, 1 minus h square r naught square, right? And then r naught cancel out. So this is, you can find the angle theta. G is constant. It means if I know the V naught, h and r naught, I can find the angle which it makes with the horizontal. Thank you students. This completes the basic concept of angular momentum, the change in angular momentum, that's impulse, the time rate of change momentum, which is called moment, and I solved some of the sample problems. My next lecture will be regarding the same topic, but I've solved some of the unsolved problems regarding the angular momentum, the change in angular momentum, which is basically the impulse, and the time rate of change momentum, which is called moment. And of course, law of conservation of angular momentum means the momentum before collision is equal to momentum after collision. I hope you understand. Please go through the lecture, solve the problems yourself, then you can understand the topic. This is lecture number 25. There will be 26. 2 more lectures will be there. Then the course will be ended. And I will tell you the topics which are to be examined in final exam. Thank you.